Hello again and welcome. Today we're going to be looking at the KAIWEETS, I guess, KM401 digital multimeter. This meter costs $30. It's a 4,000 count meter. One of the things I like about this particular meter over the last two, this one actually has a temperature input. That's a feature that I would commonly use. Let's go ahead, we'll have a look at it. Looks like they supplied it with a set of batteries. Nice little user manual. Unlike the UNI-T, this one is actually in English. Comes with a set of probes. Looks like these are fairly short. Also comes with a probably K-type thermocouple. Not a bad looking meter. It's fairly compact. Switch actually feels quite nice on this. You can see it's a little bit smaller than the Brymon BM789. Of course, these meters are not in the same class. I just grabbed some rechargeables. Let's see if she'll power up. In that last UNI-T meter I looked at, had a problem running nickel metal hydrides. You can see with this particular meter, it looks like the battery indicator is not on. You can see it here in the upper right corner. They rated this for 1000 volt Cat 3, 600 volt Cat 4, maximum 1000 volts DC, 750 volts AC. One of the nice things about this meter, you'll notice that it has a separate input jack for the low current, unlike some of the low cost meters where they share the input. So with this meter I don't have to worry about pulling a fuse. What we can do is run through a basic functional test. Again, we'll just be using our test box. It's kind of interesting, it powers up and it's in the DC mode. As long as we're here, let's try it with our 5 volt reference. You can see it reads 5.02. Let's go to AC, and this should be 2.5 volts. Looks good. So let's try it with our DC biased AC. Again, it should be 2.5. That's correct. This should be roughly 70 volts AC. Again, 56. And let's try this again in DC. This should be roughly 60 volts. And you can see it's 57. Looks good. Let's just try measuring the frequency again. This should be 60 hertz. You can see it's spot on. And let's try it with our DC biased waveform. So again, this is switching between 0 and 5 volts now at 30 hertz. And you can see it cannot pick that up. So this meter requires the zero cross. Again, an easy way to work around that is to place a capacitor in series with the input. You can just go ahead and do that real quick. This will block the DC. So there's your 30 hertz. This should be 15, and this should be 120. Let's try it in the millivolt DC mode. Does it support AC? It does not. Huh. We can use our thermocouple output. Set it 500 degrees C. This should give us roughly 20 millivolts. That appears to be working. Alright, let's try the frequency input mode. This should read it with the DC bias without any need of the external capacitor. So again, this should be 60 hertz. Let's just try it AC coupled first. And there's our 60 hertz. And this would be DC coupled 60 hertz. And DC coupled 30 hertz. 15 and 120. Yep, no problem. Alright, let's try it in continuity mode. You can see it's fairly loud. It also has this little green LED indicator. Let's see where our threshold is. This is a half an ohm. This is 1 ohm. 50 ohms, it still picks it up. Let's try it at 100. There you go. So it reads the resistance but does not trigger it. Let's go back to function. So here's diode check mode. Here's with a single silicon diode. Let's try it with 2 of them. Let's try our white LED. This should be roughly 2.5. You can see it cannot light the white LED. Let's go to resistance. And let's try it with a short. You can see it's pretty slow. Again, here's an open. And again, here's a short. A couple of seconds. Let's go ahead and we'll zero this out. Here it is with a 0.5 ohm. Sorry about the glare. And here it is with a 1 ohm. And this will be 50 ohms. and this is a 100 ohm resistor. And here's a 1K, this is a 0.1%. This is a 10K 1%. This is a 100K 0.1%. Reads a little low. This is a 1 meg 1%. This is a 10 meg 0.1%. Huh, always a little low. This is a 40 meg 2%. This is a 100 meg 5%. And you can see it over ranges. This particular meter cannot read conductance. Let's go to capacitance mode, and let's try this with a 150 picofarads. Whew, it's way off. So a trick around this is you probably could bias this thing up with some capacitance and then zero it out. Here I have a 150 picofarad mica capacitor. What I'm going to do is just place that in parallel with the input. Now what I'm going to do is zero out the meter. Now let's measure our external 150 picofarads. And you can see it's pretty much spot on. Let's try it with a 1 nanofarad. Looks good. And this is a 0.1 microfarad. Looks good. Let's get rid of our small test cap. And let's try some larger capacitors. So we'll turn off the rel. So this is a 1 mic. Again, a little slow. Here it is with a 10 mic. Again, quite slow. And here we are at 100 mic. Looks good, 103.1. Alright, let's try temperature. Again, this should be roughly 500 degrees Celsius. 507, that's good. This will be about 24, and this should be 1040. Looks like it overranges, probably at about 1000 degrees. Yep. It's got this phase input. We'll get back to that. Let's just try it with the current inputs. Again, this is going to be 100 microamps. Here it is at 10. Here it is at 1. Let's try it in the milliamp range. So again, this should be 100 microamps. That looks like it's working fine. I'm sure non-contact voltage works. It's just the light cord going up to my lamp. Let's see, it has no trouble picking that up. That's about 2 inches away. Still picking it up. That's probably 3 inches. Notice that the meter has a phase input. This is to measure three-phase power. Unfortunately, I have no way I can really test that here in the lab. Notice for the frequency, they have a range of up to 10 megahertz with a 0.001 megahertz resolution. And they say don't use it to test voltages over 250 volts AC or DC. The meter may be damaged. So what we can do is hook this thing up to our RF generator, and let's just see if it'll measure 10 megahertz. Let me go ahead and I'll set that up. Alright, so this is attached to our RF generator. Again, we'll go to frequency, and it should be reading roughly 781 kilohertz. Should be roughly 1 megahertz. Should be 2 megahertz. This will be 4 megahertz. And just an FYI, the generator is set for 0 dBm, but of course this input is not terminated to 50 ohms. What we can do is just go ahead and add a 50 ohm terminator in line with this. So ignoring the parasitics of the meter, with this terminator inserted, the meter is seeing roughly 0 dBm. It should be 8 megahertz. This is currently 9.5 megahertz. Let's go ahead and increase the output level a little bit. This will be plus 10 dBm. You can see we're picking it up just fine. And we'll go ahead and increase the frequency. And there's 17 megahertz right there, no problem. Let's just see where it conks out at. Oh, right about here. Is that the maximum we can get out of it? Let's increase the power level a little bit. So it appears with 20 DBM, the top end is about 30 megahertz with this meter. Again, pretty decent. Most people though are going to use a dedicated frequency counter. All right, you can see I have our ESD gun out. We're going to be using this for a DC power supply. You can see here they specify a maximum voltage of 1000 volts DC or 750 volts AC. It's about 700 or so. Here's 800. 900, 980, and you can see right there's 1000 volts on the meter, so it doesn't appear to have any problems reading that high of a voltage. Off to my left you can see I have one of our high voltage power supplies out. This is currently set for 60 Hertz, and if we display frequency, there you can see 60 Hertz. Now this is switching between 0 and whatever voltage I program. So you can see it's in DC. Right now we're getting roughly 12 volts. There's 34, 61. Now let's go ahead and select the AC mode. And you can see we're outputting roughly 60 volts AC. So again, this is switching between 0 and our peak voltage. Let's go ahead and turn this thing up a little bit. There's 100 volts. There's 200. 300, 400, so we'll top out at about 500 volts, no problem. What I'll do is just restrap this to run bipolar. If we go to DC volts, you can see this currently has a minus 282 volts of bias. So you can see I can adjust that now. What I'm going to do is go ahead and take this back to the AC mode. And let's start sweeping the bias and we'll see if it has any effect on our AC measurement. And you can see it does not. Wouldn't expect it would. Let's go back to the DC mode. You can see we're all the way up to a positive 170 now. Let's try adjusting this down to 0 volts. Oh, so you can see the meter's having problems with auto ranging. It's not unusual for a lot of these low-end meters. So now what I'm going to do is turn up the voltage. And you can see we're at roughly 535 volts AC. Again, this is symmetrical around the 0 point. So it doesn't look like there's anything major wrong with the KM401. Again, the auto ranging problem, I've noticed that with other meters. That was one of the things that I worked on with Bryman with this BM789 and the 786, was trying to get that auto range where it wouldn't hunt. So this meter works fairly well under these conditions. But again, for most people, this probably doesn't cause any kind of issue. So I tried to do some searches to see if there were any reviews on this particular meter. Unfortunately, I really couldn't find anything out there other than just basic unboxing and, hooking it up to a couple of simple loads. Because this is a brand I have not looked at before, I am kind of curious what this looks like on the inside. So what I'd like to do is go ahead and take this thing apart. So I assume this is just a rubber boot. Yeah. Wow, it's stiff though. You can see how it has this little lip. It fits inside of this groove. As you work around this corner here, this thing gets tight. This is probably the snuggest boot I've seen. Get around this one last corner here, I think we'd be in. There it goes. So it looks like maybe just the 4 screws in the back here. First thing we notice, you're using the full-length ceramic fuses. You can see it uses the typical cheap connectors. Again, it's a $30 meter. They have a couple of PTCs. Looks like maybe there's a couple of high-speed clamps. Maybe there's a set right here. Possibly another set up here. A couple of things that are missing. There's no surge-rated resistors. and there's no MOVs. I'm not expecting any components on the backside, but we'll just have a look. There's our little LED for the flashlight and our pickup for the non-contact voltage. You can see they have greased the contacts on this. It's got quite a sheen. Also notice some flux residue left behind. Nothing underneath the backlight. Alright, let's have a look at our switch contacts. They don't appear to be plated at all. Again, pretty much what you would expect for a $30 meter. See one small problem there. It looks like I knocked out the ball bearing. We'll have to grab the tweezers, put that back into place. And we'll just drop the ball right back down on there. And this is what our switch looks like from the bottom. Let's see if we can get the boot back on. Let's try starting from the bottom side. Might be a little easier. And if we can pull the top up and over. Yeah, that's not gonna work. Wow. Can't imagine if you just got to change fuses on this meter. It's gonna be a nightmare. Alright, let's see here if I maybe go like this. There we go. And pull it up and over. Oh, that's not too bad. And we'll push it back into the grooves. Yeah. Alright, no worse for the wear. So we're going to start out with our AC line test. Again, this generator will put out 220 volts. It's been full wave rectified. We'll go ahead and turn that on. And you can see the meter is reading roughly 240 volts DC. And in AC, you can see odd. So in AC mode, this should be reading 120 volts. Let's just check it in parallel with the Bryman. And you can see our Bryman is reading 120 volts, half of 240. Odd. Well, that's interesting. Now it's 36. And now it's 2 again. Huh. And it's still 2. Huh. I have no clue what this thing's doing. I mean, they claim the meter here is true RMS. I wouldn't think it'd have any trouble reading this. Anyway, what we'll do is, while we're applying this voltage, we'll just cycle the meter through all of its different modes, and let's see if we damage it. Alright, that's it. I'll go ahead and functional test it. KM401 survived that test just fine. So now we're going to try the grill starter. Again, I would not be surprised if this doesn't damage the meter. So I'll be applying 5 transients, both positive and negative, with the meter set to each mode, and then we'll functional test it. Ooh. We'll go ahead and flip the polarity around. Again, 5 more transients. At least with resistance, it's still reading an open. There's a chance that this thing may have actually not been damaged by this. I'm quite surprised the KM401 survived that test just fine. So next we're going to be using our homemade ESD gun to run the same test. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Here we go. Again, this gun is very close to meeting the IEC standards. Unlike our little grill starter. I wouldn't be surprised if it's not already damaged. Let's just see if it'll reset. Yeah, so far looks okay. And again, we'll go ahead and flip the leads around to change the polarity of the transient. And we'll apply 5 more. Alright, that's it. Does it still read resistance as an open? Looks like it does. Again, there's a good chance that the meter is probably undamaged. I'll go ahead and functional test it. So the KAIWEETS KM401 has survived our ESD test. What I've done is I've set up our transient generator to apply a 1000 volt peak transient. Again, this is a 100 microsecond full width half height with a 2 ohm source impedance. We'll be applying 5 transients, both positive and negative, with the meter set to each mode, and then we'll functional test it. So here we go. Outside of the Ampro BAM 510 and the Fluke 101, I don't believe we've seen a low-cost meter actually pass across this transient generator. Again, we'll just flip the leads to change the polarity. Alright, that's it. I'll go ahead and functional test the meter. So our KM401 has survived the 1000 volt transient. I've reset our generator for 1.5 kV. Again, that's a 100 microsecond full width half height with a 2 ohm source impedance. And we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Alright, okay, so our KM401 survived that 1.5 kV. Transient generator has been set up for 2000 volt peak, 100 microsecond full width half height with a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. And that's it. Alright, so the KM401 survived that 2000 volt peak test just fine. I've reset our generator for 2.5 kV. Again, that's a 100 microsecond full width half height and a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Again, at 2.5 kV, I bet you we're getting real close to where this meter is going to fail. Let's just see what happens. Okay, that's it. Alright, the KM401 survived that 2,500 volt transient just fine. I've reset our generator for 3000 volts peak. Again, this will be a 100 microsecond full width half height with a 2 ohm source impedance. This meter is doing way better than what I ever expected, just with the limited transient protection that it has. So it's just interesting, you know, $30 meter, it's doing pretty good. So here we go. And that's it. I'll go ahead and functional test the meter. We had just completed the 3000 volt 100 microsecond full width half height with a 2 ohm source impedance transient testing. I began to functional test the meter, and I'll show you what the problems are. So I currently have the temperature mode selected. This is with our thermocouple set to 500 degrees Celsius. You can see it is reading 32 degrees. This is at 1040 degrees. And here it is at 24 degrees. Also notice in resistance, this is with the leads open. This is with them shorted. Let's try it in capacitance mode. This is a 1 nanofarad capacitor. And you see it reads a over limit. This is in continuity mode. And again, you can see it's reading 74 ohms. Here it is with a short. This is in diode check mode, and you can see it's reading 0.1 volts or so drop. Let's try it in millivolt mode. Again, this should be roughly 20 millivolts. And you can see it's reading 0.3. So we've definitely damaged the meter. Let's just try it in AC volt mode while we're here. So this is 2.5. And you can see that's correct. I should have just left this boot off. Wow, that is just crazy tight. I'm guessing it's either this pair or this pair that's been damaged, maybe both. Let's just see. So that one looks okay, about here to here. Alright, so my guess is we've damaged these two transistors here. So it looks like QP and Q2. Okay, both of these transistors are a Y1. Seems to be a fairly common part that the Chinese multimeters use. Yep, that one's shorted. This one is shorted as well. Okay, so both of those are bad. Let's just see if the meter works with them now that we have them pulled. And there you have it. So it's reading an open now in the resistance mode. These paste tweezers are pretty nice. You can see how fast it was for me to pull those transistors. Again, I'm just using a wide tip. This works pretty well. I'm just going to try to freehand this. It doesn't have to be real pretty. And there you go. So now should read and open. There you have it. And we'll just stick the two blown transistors to the back of the case. Keep them out of the way. You can just see how tight that boot is. This is really bad. Good, I guess, if you don't ever have to take it apart. It's certainly easier to put it back on than it is to take it off. There we go. Again, this is with a short. There we go. So here it is with 1 ohms. Here's a 50 ohm, And here's a 100 ohm. This is a 0.01% part. Go ahead and take it out of rel. And this is a 1K 0.1%. You can see it's fine. Here's 10K. Let's try capacitance mode. And this will be a 0.1 microfarad. And here's our 1 microfarad, 10 microfarads, and a 100 microfarad. Looks fine. Go back to temperature and we'll select degrees Celsius. Again, this should be roughly 500 Celsius and 1040. Of course, it can't quite read up that high. And again, this will be about 24 degrees. So this is continuity. You can see it's reading an open. And here it is with a 50 ohm. Here's a 100 ohm. And let's put it in diode check mode. So again, here's a short. And here's a single silicon diode. And here's two in series. And again, this is going to be 60 hertz. And this will be 30 hertz. And there's 120. Let's go to millivolts. Again, this will be close to 20 millivolts. The standard DC input wasn't damaged, but here it is with a 5 volt signal. Here it is with our 60 volt signal. And here it is with our 2.5 volt signal. So yeah, meter appears to be functional again. So we just basically damaged 2 transistors that are the high-speed clamp. We got lucky this time. We didn't actually damage the main control IC. Well, that's going to be all for now. Till the next video. Hopefully we'll see you then. Later.